Today, we're going to calculate the gravitational acceleration in a very unorthodox manner using an apparatus that involves speakers, amplifiers, and a resistor in series. Let's get to deriving the theory for it. The apparatus contains a marble that is situated on the membrane of the speaker cone. We identified that the speaker membrane acts like a simple harmonic motion due to the AC signal that is inputted in. And so we shall describe the simple harmonic motion in terms of a wave equation that is set as to be y is equal to the maximum amplitude times the cosinus of omega t, where t is time. And now to identify the acceleration that the marble experiences, we shall derive this twice in terms of t. And we shall do that now. dy dt is equal to negative omega a sinus of omega t. And we shall derive this once more, since that is how we define acceleration. dy squared t squared, which is equal to negative omega squared a cosinus of omega t. Now, this is the acceleration that the marble experiences through its simple harmonic motion due to the speaker's membrane. Let's look at individual component vectors of the forces acting on the marble. We know that there's mg, the weight of the marble that's acting, and that is acting in the negative direction, which we define to be down, and the positive direction, the normal contact force with the speaker membrane. And now this can be described as n minus mg, which is equal to total force. Now, since we know the acceleration due to simple harmonic motion, so we shall multiply this by both sides due to Newton's second law to get the total force acting on the marble, which is negative m omega squared amplitude times cosinus of omega t. We shall also make an observation that when cosinus omega t is equal to exactly 1, that there exists a critical frequency for all amplitudes and for all masses such that the normal force acting on it is 0. So now let's set that condition and solve for g.
Why do you have an open banana?
Now we notice that we can cancel negative m and negative n both sides, and since that it is cosinus omega t, we set the condition to be equal to 1. We say g is therefore equal to omega squared times amplitude. And this shall be the equation for figuring out gravity. And since we know omega is equal to 2 pi frequency, that we can plug in the critical frequency in which we start when the marble loses contact with the speaker membrane. We can plug that in, and we can plug the amplitude that we find and get gravitational acceleration.
In order for us to use the equation my colleague derived, in order to find the gravitational acceleration, we should first arrive at the condition which is derived for. And that is, we want a speaker to have a signal coming in and oscillating, and then we want marble inside, and then we keep increase the frequency until we reach the point where it starts bouncing. So let me run you first through the circuit we have. We have a tone generator, which is my phone, going to an amplifier to amplify the signal, and then we have a resistor in order to control the amount of current we have, and that's going to be connected to our speaker. And as we turn it on with a marble inside, you have a marble?
It's always been here, Daddy.
Okay, so we have the marble inside, and I'm going to turn on my tone generator and the amplifier, and then we're going to observe the moment it starts bouncing. And if you approach a little bit, you can start hearing if I increase the frequency. Now I'm fixing the amplitude and I'm increasing the frequency. And you can probably hear it now. And the next step is to measure the frequency we have through my phone. We know it's 5, and we've also measured it through a musical tuner, and it gave the same frequency we have. Our last mission we have is to measure the amplitude of the membrane. But how?
But how?
The ways we can measure the oscillation of the membrane is by placing a small mirror on the membrane and getting a reflection, a laser shooting at the membrane and get it reflected on a screen, which is going to be the wall. And the idea is that when the membrane goes to a lower point, so these are the two maximums, the ray will continue to this, to this point, and then it's going to be reflected as the following. The incident angle here is going to be the same as this and as this. Now, if we draw the perpendicular line here, we're going to see that these two sides are going to be the same. And what we can measure now is this angle through doing some measurements here in the room. We can find the angle here, and we can also measure the oscillation on the screen, and I'm going to call that n. This angle here is also going to be same as this, and we also have another one, which is here. Now, if I take the cosine of this angle, that's going to be equal to x divided by m. If I go to this angle here, it's going to be, this is what we want to measure, and that's double the amplitude. That's going to be equal to the sine, or sine theta is going to be 2a divided by 8. And from the first equation, I can get rid of x, so I can say sine theta is equal to 2a divided by m cosine theta. So we will end up with a being equal to m divided by 2 sine theta cosine theta. And that's great, because now we have m, which is the oscillation on the wall, and we have sine theta cosine theta, which is an angle we can measure. So that's a way to measure a. Now, the equation we had we can further simplify this equation first by saying it's m divided by 4 sine 2 theta. So if we take this and plug it into the equation we had first for g, which is omega squared a, we can get m omega squared divided by 4 sine 2 theta. And that would be the new operational equation we work on. So now I'm going to demonstrate the measurement setup we've made for this. And we have the laser beam coming this way and getting reflected on the mirror, which we glued to the membrane of the speaker. And as we reach the desired frequency, we can start measuring the reflected ray on the wall.
But Papi, the inaccuracy of the laser pointer is greater than the oscillation. What should we do?
Welcome back to this experimental setup. So now, since we realized that the laser is a shit idea, we have to throw this back, we have to get back to the sketch. We have to throw this into the garbage and start again and use the good old method of measuring with the ruler. Now give me the back, brush. Goes to that garbage, and mirror, and the garbage.
Let me now run you through the results we've obtained in this lab. Let me now run you through the results we've obtained in this experiment. We've done this for 5 times, so we identified the critical frequency and measured the amplitude associated with each one of them for 5 times. And in front of you, you can see the results we had. And at the bottom of the table, you can see the mean value, which is 5.1 meters per second squared, and the actual value is around 9.8. And if we run a quick error analysis, we saw that the actual value of G is outside of our error boundaries. In other words, even if we take a more accurate measurements, even if we fix the laser issues and make it precise on the wall and get better results for the amplitude, it's still not going to be inside. It's still not going to get closer to the actual value of G. And this is not particularly a bad result. It just says that we have a mismatch between the theory and our experiment. So if I can show you now a simplified version of the scientific method, we have an observation, which is what happens to the marble when it starts bouncing, and then we had a hypothesis trying to explain this phenomena, and then we ran our experiment to test this explanation, and our results wasn't particularly what we expected, which can only mean one of two things. First, it could be that our experiment needs to be retaken to eliminate any random errors. It could mean that we had a factor that affected the experiment, but we didn't take into account. Or the other option could be that we need to go back to our theory and modify it, and maybe look for fallacies or assumptions that we might have taken.
Great success! Thank you for watching! Stay home!
And don't go to school.